Hello everybody. I'm going to begin a series on some SMO tips, and these are going to be tips to do very mundane sounding tasks. But surprisingly, even in these mundane tasks, there are some things that are rather clever and even one might say fun about them. And we're going to start with one of the most mundane sounding things, which is how to factor whole numbers. This does not sound like something that merits a video or even needs an explanation, but there are actually some tricks involved that are good to know. Now, the first thing that you want to know about your factorization is that you still need to know primes up to 100. And this is something that you should spend a bit of time to get comfortable with, whether by memory or just by, number sense. There are 25 of them, which I shall just write out here. So you see that we are only at 50 and we have already got to 17, and then there are not too many in the second half. So these are your primes up to 100. There are 25 of them. And I think one of the most common ones that are missed out is not 91, because 91 is 7 times 13. So this is a very commonly missed accidental prime. And this leads me to the next point, which is our divisibility test. Now, the common divisibility tests are going to be the ones that we already know. We will use the ones for 2, 3, 5, and 11. These are useful because we are testing prime number factors. And so for instance, if you have got something like 407, if you quickly test 2, 3, 5, and 11, you would realize that this passes the test for 11. And indeed, it is 37 times 11. So divisibility tests give you some quick confirmations that this or that are not prime. If you see something like 567, you can quickly say that nope, this is not prime, this is actually 3 times 183, and in fact is 3 squared times 61. The third thing that you want to be aware of is that sometimes there are obvious identities. For instance, if you get the number like 1027, this does look rather prime, but if you know that this is 10 cubed plus 3 cubed, even if you have secretly forgotten the identity for the sum of cubes, you know that there is a factorization, and hopefully you at least know that it comes with the 10 plus 3 times something. So this will confirm to you that it is actually a multiple of 13. It turns out to be 13 times 79. The ones that you want to know will be your difference of squares and the difference of cubes at the very least. You also want to recognize if something is in a very obvious form, like a plus b squared explicitly, or let's say your cube identity explicitly. Right? So if you get something that looks like that, for example, if you get 106 1208 or something like this, it looks very suspicious because this is in the form that tells you that this is actually just 100 plus 2 whole thing cubed. Now, probably these are not the places where you are in the most trouble, however. one of the most troublesome things is just simply a random looking 3 or 4 digit number. And the random looking 3 or 4 digit number can sometimes just be very difficult to factorize. The worst thing is that you're not quite sure how much time you should spend factorizing, because sometimes it isn't clear whether there are supposed to be some other factors. In order to give you a glimpse at how a decent looking speed would be like, I'm going to generate some numbers. I am going to generate 10 numbers that are between 1000 and 5000, literally some random numbers from random.org. Okay, and I have got myself here 10 numbers, but they don't really look very prime. I want one or two of them to look more prime so that I can talk about it. So let me generate another one. I think this is a decent selection. So I'm going to copy them in and maybe just increase the font size so you know that I am not cheating. So these are the 10 numbers which random.org has generated for me to factorize. Now, I'm going to do the factorization here. 3069 is divisible by 9 by our divisibility test. So it's going to be 3 squared times 341, which is also divisible by 11 based on our divisibility test. So it's 3 squared times 11 times 31. Second one, 2212. This is obviously divisible by 4. I can look at 553 and it is divisible by 7. 79 is prime, so I move on. 3350, this is a very convenient choice. The factorization is 2 times 5 squared times 67. Next one is 4603. This one is a little bit more tricky, so let me think about it for just a moment. And I can pretty confidently say that this is prime. The next one is 4863. This one is not prime, it's divisible by 3, but I will need to stare at 1621 for just a second to see whether that is prime. And it looks like it probably is prime. So that's it, it is prime. Next one is 4888. That is very obviously divisible by 8, so 8 times 611, 8 is 2 cubed. And 611 is divisible by 13. Okay, then 2305, this is 5 times 461. 461 looks prime, but let me just double check. And indeed it is prime. 1857 next. 1857 is divisible by 3. And then you have this 619. That certainly looks prime. And I am pretty confident that it is. 2394. This is 2 times 1197. 1197 is divisible by 9 as well. And this is also divisible by 7. And finally, 2979. That is also divisible by 9 times 323. Sorry, 321. 331. And 331 is also prime. So I think that's a reasonable time frame to do, let's say, 10 of these factorizations. There's a small chance that I got one of these wrong because I'm doing it without writing as much working as one would be allowed to. But you may be wondering whether there is some sort of other tricks that I have employed. Let's say when I claim that 1621 is prime, when I claim that 461 is prime, or when I, let's say, am factorizing a moderately big number like 553 or 611. There is a small trick which I like to use, well, two small tricks actually, which I like to share. Now, the first trick is that sometimes I do division from right to left. Now, this would not give you the remainder and quotient, but if you're just testing, is it divisible, that does work pretty well. Now, it works pretty well because, for instance, if I've got something like 553. Now, after 2, 3, 5, and 11, the next one I test is 7. And what I do is that I just add 7 to it. And then I say that yes, 560 is divisible by 7 because 56 is divisible by 7. So this is a positive example. If let's say I have got a negative example, like when I want to divide 461 by 7, I can also divide off 461 by subtracting 21. That doesn't change whether it's divisible, but then after that I can cancel off the 0 and say that 44 is obviously not a multiple of 7. If I wanted to divide it by 13, I could also, let's say, add 3 times 13 to 461. That gives me 500, and 500 is obviously not divisible by 13. This is the first thing that I do. It just gives me so-called twice as high a chance of having a nice next number that is obviously divisible or obviously not divisible. The other thing that I like to do is also that I like to test using difference of squares. Now, I mentioned the identities a bit earlier, but that's another thing that we have to mention. If you suspect that there are just two big prime factors, what you can do is that if you think that a number n is equal to something odd times odd, it would be possible to write that as a sum and a difference, which is a squared minus b squared. And so therefore, you can test a squared minus n to see whether it's a square, where a is just something where the square is a bit more than n. Now, you should already have a sense of what a should be like, because we know that we only test prime numbers up to the square root anyway. So for instance, you may be presented with something like 1961. And for 1961, the way that you can quickly determine that it is not prime is that if you tried 45 squared minus 1961, this is equal to 64, which is 8 squared. So it turns out 1961 is 45 plus 8 times 45 minus 8. So these are the few small tricks that you can use to speed up your calculation of whether something is prime or not. Obviously, if you then realize that it's a multiple of 7, 13, 19 or whatever it is, you still will need to proceed to do proper division. So let's say if I found that 611 is divisible by 13, I still needed to then divide it by 13. But if you remember what you just did, which for my case was to add 39 to it to get 650, then it would just be 50 minus 3. So these are just some small little tricks. Hope it's interesting, and feel free to share in the comments below if you have any other shortcuts for testing factorization or calculating factorizations. So thanks everyone for watching, and see you next time.